All right, buckle up, everybody, because today we are diving deep into general relativity. We're going to unpack this theory, figure out what it's all about, and we've got some amazing sources to guide us along the way. We'll cover the history, the main ideas, even what those brilliant minds at CERN are up to these days.
It really is amazing how far we've come since, well, Newton and that apple.
Hmm.
His law of universal gravitation, it was a good starting point, but it definitely left some huge questions hanging.
Right, like how can gravity work instantly across such vast distances? It always felt kind of weird to me. But then Einstein comes along with special relativity and the whole speed of light limit. That really threw a wrench in the works, didn't it?
It sure did. It meant gravity couldn't be just a simple force acting instantly, across the universe.
So, what did Einstein propose instead?
His big breakthrough. He realized gravity isn't a force at all. It's all about the curvature of, well, something called space-time.
Ah, there it is, space time curvature. I think I've heard of that. Isn't there an analogy with like a bowling ball on a trampoline where the ball warps the fabric?
That's actually a pretty decent way to visualize it. Think of space-time as this four-dimensional fabric that blends space and time together. And then you've got these massive objects, planets and stars. They warp this fabric. And that warping, that's what we experience as gravity.
Okay, so it's not that the Earth is being pulled towards the sun by some invisible force. It's more like Earth is following the curves in space-time, curves that the sun's mass creates.
Exactly.
Wow.
And this whole space-time curvature thing, it's not just some abstract idea. It has some very real effects, things we can actually observe.
Oh, really? Like what?
Well, one of the early wins for general relativity was explaining this tiny wobble in Mercury's orbit. It's called the perihelion precession. Newtonian physics just couldn't account for it, but Einstein's theory nailed it.
So Einstein's ideas weren't just some theory, they actually explain real stuff that had scientists stumped for ages. It's incredible that he could figure all this out just by, like, thinking about it.
He was amazing at thought experiments. He'd imagine riding a beam of light or being stuck in a falling elevator, all to explore gravity. And those thought experiments, they led him to some seriously groundbreaking ideas.
That's pretty cool. But even with all this talk about space-time curvature, it still feels a bit abstract. What does it really mean for us down here on Earth?
Well, for one thing, it means time itself is affected by gravity. Clocks run slower in stronger gravitational fields.
Hold on, you're saying time isn't constant. That sounds crazy. Does that mean time moves differently for someone on, like, Mount Everest compared to someone at sea level?
Exactly. The difference is tiny, but it's measurable. And it's actually super important for things like GPS satellites. They have to account for this time dilation to work properly.
So if GPS satellites didn't factor in Einstein's theories, our navigation systems would be way off. That makes me think about time in a whole new way. And what about those amazing images we see, of light bending around massive objects? Is that another space-time curvature thing?
It is. That's called gravitational lensing. And it's one of the most visually striking pieces of evidence for general relativity. Light from a distant star or galaxy, when it passes by a massive object, its path gets bent. It's that curved space-time again. And that bending can create these distorted, sometimes multiple images.
It's like looking through a giant magnifying glass out in space. That's amazing. Something as fundamental as light being affected by gravity in that way.
Right. It really shows how space, time, and matter, they're all connected. And that brings us to another incredible phenomenon predicted by general relativity, gravitational waves.
Oh, yeah, I've heard of those. Aren't they like actual ripples in space-time? Caused by the most violent events in the universe, black holes colliding, stars exploding. But they're super faint, right? Really hard to detect.
They are. For decades, gravitational waves were just a theoretical prediction.
Mhm.
But then in 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, they made history. They directly detected these ripples for the very first time.
It's like we suddenly gained a new sense, a way to hear the universe in a whole new way. It's mind-blowing that these waves, predicted by Einstein over 100 years ago, are now being used to study the most extreme places in the cosmos.
It really speaks to the power of human ingenuity
Mm.
and the enduring legacy of Einstein's theories.
Absolutely. But it also seems like general relativity isn't just some finished thing. There's so much we're still learning and exploring, right? Especially at places like CERN.
Yes, CERN is pushing the boundaries of our understanding of general relativity in some really fascinating ways, especially in the quest to unify it with quantum mechanics.
Ah, yes, that seems to be a huge challenge. It's like these two pillars of modern physics, general relativity for the big stuff and quantum mechanics for the tiny stuff. They don't quite fit together, do they?
You put it perfectly. This unification problem, it's been one of the biggest challenges in physics for decades.
So, how are scientists at CERN trying to tackle it? I've heard things about string theory and loop quantum gravity. What are those all about?
Well, those are some of the leading contenders for a theory of quantum gravity, a theory that could potentially bridge that gap between general relativity and quantum mechanics.
Okay, let's start with string theory. What's the string all about?
Okay, so imagine this. Everything in the universe, the smallest particles, the biggest galaxies, they're all made up of tiny vibrating strings. These strings are so unbelievably small that they look like point-like particles to us. But their vibrations, those give rise to all the different forces and particles we see.
So, it's like a cosmic symphony with each string playing a different note that creates a different particle or force.
I like that. A beautiful analogy. And here's the remarkable part. String theory, it naturally includes gravity. One of the ways these strings vibrate corresponds to the graviton, the hypothetical particle that carries the gravitational force.
So, string theory could be a way to unify gravity with the other fundamental forces. That's huge.
It is. It's a really ambitious theory. It's still being developed, but it has the potential to revolutionize our understanding of the universe.
Okay, and what about loop quantum gravity? How does that try to solve the unification problem?
Loop quantum gravity takes a different approach. Instead of strings, it suggests that space-time itself isn't smooth and continuous, like general relativity says. It's got a granular structure at the tiniest scale imaginable.
So, instead of a smooth fabric, space time is more like a network of, well, interconnected loops.
Exactly. Those loops, they're the fundamental building blocks of space-time. And their interactions, they create the gravitational force.
Wow, this is getting pretty abstract, but I think I'm starting to get a sense of what these theories are about. It's like scientists are searching for the missing pieces to complete our picture of the universe.
That's a great way to put it. And CERN is playing a crucial role in this puzzle solving, both through theoretical work and with the experiments at the Large Hadron Collider.
Speaking of the Large Hadron Collider, I've heard they're actually trying to create mini black holes there. Is that true?
It's a possibility. But it's important to say that these mini black holes would be incredibly tiny, and they'd evaporate almost instantly. But if we did create them, monumental discovery. It would give us a peek into the extreme conditions where gravity and quantum mechanics collide.
Wow, it sounds like we're on the verge of some truly groundbreaking discoveries. And it all comes back to that fundamental shift in how we understand gravity, thanks to Einstein and his theory of general relativity.
Absolutely.
What?
General relativity hasn't just changed how we see the universe. It's opened up entirely new avenues of research, research that keeps pushing the boundaries of what we know.
And on that note, I think it's time for us to take a little break. When we come back, we'll dive even deeper into the mysteries of black holes and explore some of the most intriguing questions that arise from their very existence. Stay with us.
Welcome back to our deep dive. Yeah, before the break, we were talking about some really intriguing questions. Questions that come up when you start thinking about gravity as the curvature of space-time.
Yeah, we were getting into dark energy and dark matter. These mysterious forces shaping the universe. It's incredible. We can see their effects, but we still don't really know what they are.
It really shows how much we still have to learn about the cosmos. It's exciting, though. These mysteries, they drive science forward, pushing us to develop new theories, new technologies.
Speaking of new theories, we touched on string theory and loop quantum gravity earlier. Those are some pretty mind-bending concepts. Can you give us a bit more insight into what they're all about?
Sure, both string theory and loop quantum gravity, they aim to reconcile general relativity with quantum mechanics, which, as we mentioned, has been a major challenge in physics for decades.
Yeah, because they seem to describe the universe on such different scales, right? General relativity for the really big stuff, planets, stars, galaxies, while quantum mechanics governs the super tiny stuff, atoms, particles, the subatomic world.
Exactly, and these two theories, they're both incredibly successful in their own domains, but they don't quite mesh together. That's where string theory and loop quantum gravity come into play.
Okay, so let's start with string theory again. Remind me, what's the string all about?
At its core, string theory proposes that the fundamental building blocks of everything, not point-like particles, but tiny vibrating strings. Imagine them like guitar strings. But instead of musical notes, they create the particles we observe.
So different vibrations create different particles, electrons, quarks, photons. They're all just strings vibrating in different ways.
Precisely. And the remarkable thing is, string theory naturally includes gravity. One of the ways these strings can vibrate, it corresponds to the graviton. that hypothetical particle that carries the gravitational force.
So string theory could be the key to unifying gravity with all the other fundamental forces. Electromagnetism, the weak force, the strong force. That's a pretty big deal.
It is. Potentially, it's a theory of everything, a framework to explain all the fundamental interactions in the universe. Of course, there are still many challenges, open questions in string theory, but it's a very active area of research.
And what about loop quantum gravity? How does that tackle this unification problem?
Loop quantum gravity takes a different approach. Instead of focusing on strings, it quantizes space-time itself.
Quantizes space-time. Does that mean it breaks space-time down into, like, discrete chunks? Like pixels on a computer screen?
That's a good analogy. Loop quantum gravity says that space-time isn't actually smooth and continuous like general relativity describes it. It's got a granular structure at the Planck scale, the smallest possible length scale in physics.
So instead of a smooth fabric, space-time is more like a network of interconnected loops.
Exactly. These loops are the fundamental building blocks of space-time, and their interactions give rise to gravity.
This is all pretty abstract stuff, but I think I'm getting the general idea. So both string theory and loop quantum gravity are trying to bridge the gap between general relativity and quantum mechanics. But they're coming at it from different angles.
Ugh.
String theory with these tiny vibrating strings, and loop quantum gravity with quantized spacetime itself.
That's a great summary. And it's important to remember, these are still theoretical frameworks. We don't have any definitive experimental evidence to prove or disprove either one yet.
But CERN is working on it, right? They're trying to find ways to test these ideas to see which one, if either, holds water.
Absolutely. The Large Hadron Collider is an amazing tool for probing the fundamental nature of the universe. And it could give us some clues about string theory or loop quantum gravity.
So what kind of evidence are they looking for?
Well, one possibility is finding supersymmetric particles. Supersymmetry, it's a key prediction of string theory. It suggests there are partner particles for every known particle in the standard model of particle physics.
So if they find these supersymmetric particles, that would support string theory.
Exactly. That would be a major breakthrough, a strong indication that we're on the right track.
And what about loop quantum gravity? Are there any experimental signs that could support that theory?
One prediction of loop quantum gravity is that the speed of light might actually vary a little, depending on the energy of the photon. It's a very subtle effect. But with sensitive enough instruments, it could be measurable.
So the search is on. CERN is right at the forefront of this quest to unify general relativity and quantum mechanics. It's so exciting to think about the discoveries that might be just around the corner.
It really is. And it's not just about finding the right theory. The process of exploration itself is so valuable. By pushing the boundaries, asking these fundamental questions, we're deepening our understanding of the universe and our place in it.
And speaking of our place in the universe, let's bring it back to general relativity and its impact on cosmology. Earlier, we talked about the expansion of the universe and those mysteries, dark energy and dark matter. How does our understanding of gravity shape how we see the cosmos on the grandest scale?
General relativity gives us the framework to understand the evolution of the universe. It tells us the universe isn't static, it's dynamic, it's expanding. And that expansion, as we discussed, is accelerating, driven by this mysterious force we call dark energy.
Right. And we still don't know what dark energy is, but we can see what it's doing. It's like this invisible hand pushing everything apart.
Precisely. And then there's dark matter. We can't see it directly, but we know it's there because of its gravitational effects on galaxies. It's like an invisible scaffolding, holding the universe together.
Wow, so we have these two invisible things, dark energy and dark matter, and they're shaping the fate of the cosmos. That's a pretty mind-blowing thought.
It is. It just shows how much we still have to learn about the universe. We're like explorers charting a vast, uncharted territory, constantly finding new and unexpected things.
And CERN, it's like our base camp, providing the tools and the expertise to guide us on this incredible journey. It's not just about smashing particles together. It's about unraveling the deepest secrets of the universe and understanding our place in it.
I love that. Beautifully put. And it's important to remember this journey is for everyone. Science isn't just for scientists. It's a shared human endeavor. Everyone can share in the wonder of discovery, the thrill of exploration, the pursuit of knowledge.
Absolutely, and that's what we're trying to do here on Deep Dive, to spark that curiosity, to ignite that passion for understanding, to share the awesome beauty of the universe with everyone.
Well said. And as we continue our exploration of general relativity, let's keep that spirit of curiosity and wonder alive. There's still so much to discover, so many questions to ask, so many mysteries to unravel.
Okay, so we've journeyed from Newton's apple to Einstein's mind-bending spacetime. from the expanding universe to those mysteries, dark energy, and dark matter. And now I think it's time to step into perhaps the most intriguing phenomenon predicted by general relativity: black hole.
Black holes, they're regions of space-time where gravity is just so strong that nothing, not even light, can escape. Like cosmic sinkholes, they warp space-time so much that anything crossing their event horizon, that point of no return, it's trapped forever.
So once something falls in, it's gone. But doesn't that kind of clash with, well, basic physics?
You're hitting on the information paradox. One of the fundamental principles of quantum mechanics is that information can never be truly destroyed. But classical general relativity, it suggests that information falling into a black hole is lost forever. So yeah, we have a bit of a puzzle here.
So either information is lost, which breaks quantum mechanics, or something weird is happening at the edge of the black hole that we just don't understand yet.
Exactly. And that's where a lot of the exciting research and theories come in, like Hawking radiation.
Right, we touched on that earlier. Can you remind me how that works again?
Sure. So according to Stephen Hawking's calculations, black holes, they aren't completely black after all. Because of quantum effects near the event horizon, they actually emit a faint thermal radiation.
So black holes are like slowly leaking energy. Does that mean they could eventually completely evaporate?
Precisely. If Hawking radiation is real, black holes slowly lose mass and energy over time. It would take an incredibly long time for a typical black hole to evaporate entirely, but theoretically it's possible.
That's wild. But if they evaporate, what happens to all the information they've swallowed? Does it just disappear, or does it come back out somehow?
That's the big question. Hawking initially thought the information was lost, which was a pretty radical idea. It challenged the very foundations of physics. But later, he changed his mind. He proposed that the information might be encoded in the Hawking radiation itself.
So maybe it's not totally gone, just scrambled up and radiated back out into the universe.
That's one possibility. But it's a really tough problem to tackle, both in theory and in experiments. Hawking radiation is incredibly faint. We've never directly observed it.
So any other ideas about how this information paradox could be solved?
There are. One fascinating idea is the holographic principle. Imagine that all the information inside a black hole, it's not actually inside, it's encoded on its surface, on the event horizon.
Wait, so it's like a hologram? The information is projected onto a two-dimensional surface, even though the object itself is three-dimensional.
Exactly. It sounds counterintuitive, but the holographic principle suggests that the universe might be more like a hologram than we realize.
That's seriously mind-blowing. But how does that help with the information paradox?
Well, if the information is on the event horizon, then it's not really lost when something falls into the black hole. It's just transformed. And since the event horizon is a two-dimensional surface, the information isn't lost, even though it seems like it is from our three-dimensional perspective.
Okay, I think I'm starting to get it. It's like burning a book, right? The information isn't really gone, it's just been transformed into smoke and ash.
That's a great analogy. And just like we can analyze the smoke and ash to learn about the book, physicists are trying to understand how information might be encoded in Hawking radiation or on the event horizon of a black hole.
So black holes aren't just these cosmic vacuum cleaners. They could be revealing some deep secrets about information and the universe itself.
Absolutely. And they highlight how interconnected different areas of physics are. We can't understand black holes without thinking about quantum mechanics, information theory, even thermodynamics.
It seems like every time we answer one question about black holes, 10 more pop up.
That's the beauty of science. Every discovery leads to more questions, which drives our curiosity, our quest for knowledge. And general relativity, it's been an incredible guide on this journey. It's shown us how gravity shapes the cosmos, from the largest scales to the incredibly small.
It's been a wild ride, that's for sure. Through this warped and wonderful world of general relativity, we've seen how Einstein's ideas revolutionized our understanding of gravity, leading to these mind-bending concepts like space-time curvature, time dilation, gravitational lensing, gravitational waves, and of course, the enigmatic black holes.
So we've covered a lot, but it's really just the tip of the iceberg. General relativity is still a source of inspiration and wonder, driving countless research projects and pushing the limits of human understanding.
So to all our listeners out there, keep exploring, keep questioning, keep marveling at the universe and the laws that govern it. Because as Einstein said, the important thing is not to stop questioning. Curiosity has its own reason for existing.